Welcome to Math 355 Abstract Algebra. This is lecture 7. And so we're going to continue to do today is do more on ring theory. So last time, this was the problem solving session and section 1 had the theory lecture. Now today you guys get the theory lecture and you should then watch later the problems that we did in section 1. So we did some really nice ones to highlight how do you attack problems, really going into incredible detail, which you could not normally do in a class when you have to cover all the content. So this is going to have you generally watch more videos and do a little bit more work, but I think the dividends are high. Because this is a trial for the first week, since you're doing 2 extra classes, there will be no classes next week. So you can use that as a little way to get caught up and everything else. All right. So just to quickly review, especially since this was done in the other section, a ring is a set with 2 operations, which we'll often call addition and multiplication. We'll denote with a plus and a dot. And so it has the following set of rules. The first is that R is a abelian group under addition. So we typically never use the plus sign unless it is going to be an abelian group. It's not a requirement, but it's nice if everybody tries to use the same conventions. I believe we have people who are taking economics. You're auditing economics? Okay. If you do a supply-demand curve, does it matter which axis is price and which axis is quantity? Does it matter for the universe? No, but if you use the opposite convention from everyone else, you will be shot, and for good reason. Because when people glance down at what you have, they're going to be misinterpreting it because they're going to be casting it into what they're used to. So whenever possible, you want to have good conventions that everybody follows. So typically, if I write plus, it should be an abelian group. The next is with multiplication, it's almost a group. The elements are not required to have inverses. Since we want to have a 0 element, it's not surprising that 0 will not have an inverse. What's interesting is there may be situations where everything has an inverse but 0. And in that case, then it's almost a multiplicative group. And what you could then say is, let's look at the non-zero elements and show that that is a multiplicative group. So there's an identity element 1 sub r, which basically satisfies whenever you multiply by it, you get back what you started with. So it's a multiplicative identity. And then we have the additive identity 0 sub r. And then we have the associative law holds. And then we have the 2 different forms of the distributive law. Do we do things on the left or do we do things on the right? It would be great if the multiplication was also commutative, but that is not required to hold. But in almost all the problems we're looking at, it will say you assume is commutative. All right, so the first is just doing some more examples. So a nice example is matrix rings. So we have, in this case, A, B, C, and D are real numbers, and we look at the set of 2 by 2 matrices. That's what the subscript 2 means, whose entries are real. And so how would you add 2 matrices? So if you have A, B, C, D, and you have alpha, beta, gamma, delta, how would you add them? Yeah, just add them component-wise. A plus alpha, B plus beta, C plus gamma, D plus delta. And then if we want to multiply A, B, C, D, alpha, beta, gamma, delta, if we want to multiply them together, this is a little bit more involved. This is our rule for matrix multiplication. It would be A alpha plus B gamma, and it would be A beta plus B delta. Then it would be C alpha plus D gamma, and then C beta plus D delta. Now, I can be like Moses coming down from Mount Sinai with laws from God and just say, and this is how we shall define matrix multiplication. And if I define matrix multiplication like that, then it's going to be closed, and you can go and you can show that it will have all the properties you want. It will be associative, there will be an identity. So we can use this as our definition of matrix multiplication. It turns out this is the natural definition to have because we want essentially, A, B acting on V to be the same as this matrix A, B acting on V. And so in the first one, we first act on B by B. That's the new vector. Then we act on that by A. There should be some matrix which is the same as that iterative two-step process. And that's what leads to this as the definition of matrix multiplication. So you can go through and you can show that this satisfies all of the conditions. Will the matrices be necessarily invertible? No. And so if you write down some matrices, you will, without too much work, find a matrix that's not invertible. So anybody want to give me a non-invertible matrix? Yes. And now give me a non-zero non-invertible matrix.
By that you mean none of the entries?
No, I just mean it's not the zero matrix. So modify your answer as little as possible. Oh, you're going to put the one there? I'm glad you said put it wherever there's other things you could have said. So, you always try to find what's the simplest example I can find. And so here are some really good, simple examples. What if I just tried the matrix 1, 2, 3, 4? Is that invertible? Yes. This is invertible. But if we, again, we're not doing this in this problem. If I give you this matrix, it's not invertible. And as a fun exercise, if I give you an n by n matrix where the numbers go from 1 to n squared, none of those will be invertible once n equals 3. So just a nice example of you sometimes have to be a little bit careful when you throw things down. Almost any matrix you throw down should be invertible if I just throw down random entries. But when I'm using integers, then that's very different. I could have catastrophic alignment. And with 1, 2, 3, 4, 5, 6, 7, 8, 9, there's a catastrophic alignment. As a nice exercise, try to think, why is that matrix not invertible? Well, what happened if I looked at the n by n model of that? Okay. So we also talked about a ring homomorphism. So ring homomorphism is a map from R to R prime with the following 3 properties. It sends the identity to the identity. So it's not necessarily the same identity element. It's the identity in R goes to the identity in R prime. Phi of a sum is the sum of the phis. Phi of a product is the product of the phis. And then we showed as a consequence that it also sends the 0 element to 0. So also sends 0R to 0R prime. But we don't need that as a defining characteristic of a ring homomorphism. We just get that for free. The kernel of phi is the set of all elements that are sent to 0. And by the remark I just said, we know that 0 is at least in this. So the kernel of phi is at least non-empty. And then what would you love to know about the kernel of phi? So it's definitely a set. So is it a group? But where does the kernel of phi live? It lives inside what? I'm sorry? Kernel phi is a subset of what? R. So you shouldn't be asking, is it a group? You should be asking, is it a ring? Is it a subring of R? So you could ask, is it a group under maybe addition? But actually, more than that might be true. Hopefully you can show that it is a subring of R. And we can go through and just do the standard calculations. All right. So one of the things that I've tried to stress is you want to have a couple of go-to examples in anything you're looking at. As we talked about, there's always a trivial group homomorphism from G to any other group. What's the trivial homomorphism? Send everything to the identity, right? So if I send everything to the identity, I'm going to trivially get a group homomorphism. And so it's worth asking, well, Z is a ring, and whenever I need an example of a ring, Z is one of the ones I should go to. The next example I would go to are the clock groups. But Z is a very natural ring. So what kind of homomorphisms, what kind of ring homomorphisms can I have between Z and an arbitrary ring R? So example 3.9, and you could have easily made this a lemma or a proposition instead of example. It says, for every ring R, there's a unique homomorphism from Z to R. So what this is telling us is that if I want phi to be a ring homomorphism, there's one choice and one choice only, and that choice will work. And we start off by we know a couple of things. We know because it's a ring homomorphism, phi has to send 1 to the identity element in R. And this is why it's actually really good here to use the subscript R to remind ourselves that the output is not an integer, it's just something in this ring R. Maybe R is one of my matrix groups. And we know that phi has to send the 0 element to the 0 element. So what we need to do is we need to show that this now defines phi on all the integers. These two are forced on us. So these are forced on us as phi is a ring homomorphism. So we must find phi of n for all n and z. So what do you want to look at? We know phi of 0, we know phi of 1. What should we look at next? Okay, so we want to look at phi of 2. So phi of 2 is phi of 1 plus 1 is phi of 1 plus phi of 1 is 1r plus 1r. So that's basically just 2 times 1r. What should we look at now? Phi of 3, and that will be phi of 2 plus 1. That's phi of 2 plus phi of 1. That's 2 1r plus 1r, which will just be 3 times 1r. How should we handle things in general? What do we do now? So what's the process? Induction. So induction. Base case done. Assume phi of n is n times 1r. Then phi of n plus 1 is phi of n plus phi of 1 is n times 1r plus 1r is n plus 1r times 1r. So does this determine phi for all the integers now? So it determines phi for all the positive integers. We now need phi for the negative integers. How can we get phi for the negative integers? So we know phi for every positive integer. What could we look at to get phi of a negative integer? Okay, so 0 equals phi of 0. And how would you want to rewrite 0? So n plus minus n. So that'll be phi of n plus phi of minus n. Therefore, phi of minus n is negative phi of n. And we interpret this as phi of n plus phi of minus n is the additive identity 0. So that means phi of n is the additive inverse of phi of minus n. And that is how we can interpret what is going on here. So now we know phi for all integers. So phi is well defined and have 0 freedom. In choosing it. So because phi of 0 has to be 0 and phi of 1 has to be 1, because it's a ring homomorphism, all the other values are forced on us. So we've just shown that there is always a ring homomorphism between the integers and R. Instead of looking at the integers, I could put in another ring. What would be an interesting ring to put in? Let's put in one of the clock groups. So as an exercise, try to find, say phi from Z mod MZ to R. Maybe M is prime, maybe not. So that would be a good thing to think about. We just had remarkable success. Maybe no matter what I give you, there's only one ring homomorphism. Life would be kind of boring if that was the case. And that maybe if the rings become more complicated, you might have more possibilities, more things that you can do. But it's quite telling that for the integers, there's only one possibility. Well, now that we have that, let's look at some other things. So try looking at Z mod MZ. And maybe it's the case that the answer depends on M. If M is prime, things are nicer than when M is not prime. So that could come into play, or maybe it doesn't. But again, I'll leave that for you to think about. Okay, so now we're moving on to section 3.4, special types of rings. So a field is a commutative ring with a property that every non-zero element has a multiplicative inverse. Doesn't it seem wrong to you to exclude zero? We're letting everything else have a multiplicative inverse, but zero does not. What would it mean if zero had a multiplicative inverse? Have we seen anything like that? It might have been done in the other section, but you're supposed to watch the video. There is an example of a ring where zero has a multiplicative inverse. Yeah, when the ring is just zero. If the only element is zero, closure is easy, associativity is easy, everything times anything is just still zero. So if you have the ridiculous situation where your ring is just zero, then zero is both the multiplicative and the additive identity. Zero does have a multiplicative inverse itself. We really don't want to concern ourselves too much with studying the ring that has only one element, the zero element, right? It's kind of boring. But you do have to be aware that something like that could happen. So it is possible to have a ring where zero is invertible. In general, however, we do not expect zero to be invertible. And so the weakest thing we can say is that if you just take every element that's not zero, then they have an inverse. And if that happens, we call it a field. So there could be situations where some of the non-zero elements are invertible. Can you give me a situation of a ring where some of the non-zero elements are invertible, but not all? Okay, where some non-zero are invertible. So you said matrices. Good, so 1, 0, 0, 0 is not invertible. And it's not the zero element. But let's say 1, 2, 2, 5 is invertible. So who can give me the inverse of this matrix? So
5,
yes, 5, -2, -2, 1. So for 2 by 2 matrices, we actually have a nice explicit closed form expression for this. This was not a randomly chosen matrix. I chose a matrix where the determinant was 1 so that I would have my entries be integers. So I can give you a 2 by 2 matrix which is invertible, but maybe its inverse is not with integer entries. So am I looking at 2 by 2 matrices over the real numbers or over the integers? depending on where you study something, it may or may not have an inverse. So 1, 2, 2, 5 has an inverse over both 2 by 2 matrices with integer entries and real entries. But if I gave you 1, 2, 2, 3, actually 1, 2, 2, 3 would also work. If I gave you 1, 2, 2, 7, that would not have a inverse over integer matrices. Can somebody give me another example where you can have non-zero elements? Oh, so this is a given where some non-zero are invertible, some are not. So can you give me another example where some non-zero elements are invertible and some non-zero elements are not invertible? So this has to be one of your go-to examples. Clock arithmetic. So if I look at, Z mod 12Z, 5 inverse is what? 5. And 7 inverse is 7. 11 inverse is 11. But 2, 3, 4, 6, 8, 9, and 10, not invertible. So here's an example where some of the non-zero elements are invertible, some of them are not. So a field just means that every non-zero element has a multiplicative inverse. What you can always do is you can restrict a little bit, and you can say, let me look at the subset of elements that are invertible. Is it hard to show that if you restrict yourself to the subset of elements that are invertible, that everything is invertible? So if I restrict to the subset of invertible elements, will they all be invertible? Yes, why? Because we're restricting to that, right? So it may be the situation that, okay, my ring is too large. I have some elements that are not invertible. Let me restrict to the elements that are invertible. Is that a ring? So here, I'd be looking at Z mod 12Z, but only look at the elements that are invertible, 1, 5, 7, 11. If I add 2 of those elements, is it still going to be in 1, 5, 7, 11? No. So if I restrict to just the invertible elements, I'm not guaranteed that I'm going to be able to form a ring. I'm going to start to lose things. But maybe I could look at the multiplicative group of invertible elements, and maybe that's worth studying. So it's always a question of how much do you have to throw away and what structure remains. So let R be a commutative ring. So we keep having to remind ourselves that R is a commutative ring for a lot of these properties. An element A is called a zero divisor if A is not 0, and there is some non-zero B in the ring such that A times B is 0. You're an integral domain if you have no zero divisors. So in the definition of a zero divisor, we say that there is a non-zero B such that A times B equals 0. Why do we insist that B has to be non-zero? Why can't we say there's some B such that A times B equals 0? Yeah, if we take B equals 0, then A times 0 is 0. So if the definition of a zero divisor just said that there is some B such that A times B equals 0, just take B equals 0, and we would see that if this was the definition, every element is a zero divisor. If every element is a zero divisor, is this a useful concept? No. So you always want to think, why did we choose this definition? Where is this definition coming from? It's basically, I want to extract a subset of the elements to study further. I don't want to look at everything. I want to look at elements that have an additional property. And so here, the idea is I want some non-zero elements such that A times B equals 0. Now, why am I not worrying about also showing that B times A equals 0? Because we're assuming it's commutative. But we also, in this class, when we did the problems last time, we said, well, look, if you have a right inverse, you have a left inverse. And we did not need to assume commutativity for that. But again, we're assuming R is commutative. We don't have to worry about that. It's enough to just find a right inverse. So can anybody think of a situation where you have two elements that are not zero, but their product is zero? And now we can actually go back to the examples from before as to why I did not like your example. So let's consider 2x2 matrices with integer. I think we're doing real entries. With real entries. If I take 1, 1, 0, 0, and I take 1, 0, 0, 0, and 1, 0, 0, 0, what do I get when I multiply them together? We just get back itself. So this is called an idempotent matrix. A squared equals A. There are other matrices that square to themselves. Can you give me another matrix that squares to itself? 0, 0, 0, 1. Hello? Okay. So we could have a 1 in the bottom right corner. What else could we do?
Oh, yeah. 1, 1 on the
So we could do 1, 1 on the diagonal. There's something else we can do.
or non-zero.
You're all being biased. You're only looking at certain types of numbers. Is there anything else we can use? Does anything else square to 1? Or is this all that we can do? Are these the only possible matrices? But that's not also now that's interesting. So what if you tried to do 1/2? So what if you took the matrix 1/2, 1/2, 1/2, 1/2, 1/2, 1/2, 1/2, 1/2? What do you get when you multiply? You get 1/2, 1/2, 1/2, 1/2. So was this what you were thinking of when you said 1/2? Yeah, very good. This is not just ones and zeros. Something more is going on here. So, what is an idempotent matrix? Well, there's only 4 entries for my matrix. I square it. I've got your 4 equations for unknowns. Let's try to find all the solutions. So, a nice problem is find all idempotent 2x2 real matrices. Now, let's consider the example I wanted to do, 0, 1, 0, 0. And I wanted to do that because as the professor, I know where the lecture is going, and having that in the beginning. What happens when you multiply that matrix by itself? What do you get? So this will just be all zeros. We say A is nilpotent if some power of A is the zero matrix. So here, A would definitely be a nilpotent matrix. And so it's an example where if it was A cubed was the zero matrix, then A times A squared would be 0. And that would prove that A is a zero divisor. So matrices can give you some really nice examples of situations where you have zero divisors. Can you give me another example where we might have zero divisors? What else could we look at? Well, no, not in terms of matrices. Give me another example. Yeah, clock. When in doubt, your go-to example should be the integers, the clock groups, matrices. Try it on these. So consider, Z mod MZ where maybe M equals A times B, well, sure, with, A, B greater than 1. So do you think a clock group with a composite number of hours, do you think that has 0 divisors? Yeah. So find x and y not equal to 0 such that x times y equals 0 mod m. What could you take x to be? And y? And if you wanted to be contrary, what could you take x to be? If you didn't want to take x to be A, you could take x to be B, right? And you could then take y to be A. Those are the only choices we know have to work, right? We know those will work. If I gave you, m equals 12, I could do 3 times 4. I could do 2 times 6. I could do, of course, 4 times 3. I could do 6 times 2. Those are the only real possibilities. So if m is composite, depending on how many ways you can factor m as a product of 2 composite numbers, as the product of 2 numbers greater than 1. It's okay if one of the numbers is prime, that's fine. But every way I can factor it is going to give me more examples. Okay, so we know that there are definitely going to be situations where we can have 0 divisors. It turns out if m is prime, then no 0 divisors. And we basically did that in the first section today. And we might talk a little bit about that here later. So if there are 0 divisors, the only way that can happen is if m is composite. Okay. So really what's lurking on in the background is what's called the cancellation property. That if we have a commutative ring R, and again, it's annoying to constantly be saying commutative ring, commutative ring, commutative ring, but not every ring has to be commutative. Can you give me an example of a non-commutative ring? Where it's not commutative under multiplication. Matrices, go to examples. We don't have that many. Integers, clocks, matrices. Oh, good. Okay, matrices is already enough to give me a counterexample. So we know that not every ring is going to be commutative. So you always want to ask, how important is it for the ring to be commutative? So a commutative ring is said to have the cancellation property if for every choice of A, B, and C, the following is true. If A times B equals A times C, then B equals C or A equals 0. And a commutative ring has this cancellation property if and only if it is an integral domain. What this is basically saying is you can do what you would like to do. If you see AB equals AC, you want to basically say either A is 0, in which case, of course, the equation is true, or B equals C, in which case it's a triviality. Can you give me an example where this is not true? A ring that doesn't have the cancellation property. So what would be an example where you don't have cancellation? Well, it says a commutative ring has the cancellation property if and only if it is an integral domain. We haven't proven that yet, but that's what it wrote. So if you're going to search for a counterexample, you better be searching among rings that are not integral domains. So you need to find a ring that has divisors of 0. Do you know any examples of rings with divisors of 0? Z mod 12Z. So let's go back to our clock. So if I look at Z mod 12Z, can you give me example? I want AB equals AC, but A is not 0 and B does not equal C. So can you give me 2 products that are the same mod 12, but B does not equal C and A is not 0.
3 times 4 is 8.
Okay, so 3 times 4 equals 3 times 8 mod 12. And 3 does not equal 0, and 4 does not equal 8 mod 12. So we at least know that the cancellation property is not always true. So we cannot always multiply. Well, essentially, what do we want to do? We want to multiply by A inverse. Why can't we just multiply by A inverse? Why can't we just multiply both sides by the multiplicative inverse of A? Yeah, we don't know that the multiplicative inverse exists. The definition of a ring does not require the multiplicative inverses to exist. Okay, so now let's look at the proof. So if AB equals AC, that's true if and only if AB minus AC equals 0, which is true if and only if A times B minus C equals 0. So these are all equivalent. If AB equals AC, I can always add the additive inverse to both sides, and then I can use the distributive law. Okay. So now, if you're an integral domain, what does that mean if A times B minus C equals 0? So if R is an integral domain, then no divisors of 0 thus, if A times B minus C equals 0, either A equals 0 or B minus C equals 0 or both. Therefore, A equals 0 or B equals C. So if we're an integral domain, then it's clearly the case. So we've just shown one direction. We've just done this direction. Assuming it's an integral domain, we've then proven it has the cancellation property. Now we want to do the other direction. If R has the cancellation property, must show R is an integral domain. Okay, so how would we show that it's an integral domain? So we want to show that if we have a product that equals 0, either x or y equals 0. So must show if x times y equals 0, either x or y is 0. Does everyone agree that this is what we have to show? Right? How can we do this? We need to somehow use the cancellation property, right? We somehow have to have an AB equals AC. Yes, because that's just simple subtraction. Yes. But you have to tell me A, B, and C. Right. What should A, B, and C equal?
X and Y
Equals 0.
X and Y are non-zero.
Mm-hmm.
Therefore, we can take A as X.
Good. So try A equals X, B equals Y, and what should C equal? 0, yes. Then you get X times Y equals X times 0, right? Because we're assuming XY equals 0. So by the cancellation property, as X does not equal 0, we have Y equals 0. We're done. So if you're an integral domain, you have the cancellation property. If you have the cancellation property, you are an integral domain. For a lot of these problems, it always comes down to which is the easier direction to prove. These are now equivalent. If I show something has the cancellation property, I immediately have it's an integral domain, and now it has all the properties of an integral domain. If I show something is an integral domain, I immediately know it has the cancellation property, and I have all those properties as well. So these two properties are equivalent. And once you have one, you have the other. When you're trying to prove one of them, sometimes it's easier to show the cancellation holds, sometimes it's easier to show it's an integral domain. Okay. So now, unit groups and product rings. So let's let R be a commutative ring. The group of units is the subset defined by, it's the set of all A and R, such that there is some B, such that A times B equals 1. So the group law on R star is ring multiplication. The elements of R star are called units. And so we're using the star to denote the invertible elements. All right. Now, I'm only saying that there's some B such that A times B equals 1. Why am I not saying that B times A equals 1? So why am I only saying A times B equals 1? Why am I not saying that B times A equals 1? It's commutative, right? Since it's commutative, I don't have to worry. Once I have one direction, I have the other. So proposition 317 is the set of units is a group under multiplication. So what do we have to do to show something is a group? Identity, what else? Inverses. So we have identity, closed, and associativity. Okay. So proof. Do we have an identity? Is there an identity element? Yeah, I mean, because R is a ring, it comes with a multiplicative identity. Yes. The multiplicative identity of R. What about associativity? Does it have associativity? Yeah, it's inherited. Okay. The next ones are closure and inverses. Okay, let's do inverses. If A is in R star, is A inverse in R star? Yes. So if A is an R star, that implies there exists a B such that A times B equals 1. So what do we know about B? So B is the multiplicative inverse of A. But if AB equals 1, that implies BA equals 1. So A inverse times A equals 1. So there exists an element, let's call it X, such that A inverse times X equals 1. Just take X equals A. Being a little bit pedantic here. But this does show that we do have the inverse. Okay. And the inverse is still going to be in the same set. We're looking at elements that are invertible. A inverse is invertible. Need to show A inverse is in R star. It's not enough that A inverse exists. This is a really subtle point. In fact, I just emailed the author on this and the need to be very careful here. It's not enough that A inverse exists. It has to still be in the set that we're looking at. Okay, well, where are we living? We're living in the set of elements A such that there's some B on the right, such that A times B equals 1. So we need to show A inverse is an R star. But what does A inverse equal? So what is the inverse of A inverse equal to? A. So since A inverse equals A, and we assumed A is an R, then we're good. Okay. And then the last thing is closure. So let's say A1 and A2 are an R star. So there exists B1, B2, such that A1, B1 equals A2, B2 equals 1. Then what do you think the inverse of A1, A2 would be? B2, B1. That's actually a very nice way of writing it, because if I write it like that, B2, B1, if I start doing associativity, this is A1, A2, B2, B1. I'll do it like this. And what's A2, B2? 1. So I'm going to just, it's A1 times B1 just to be safe, which is just 1. What's interesting is because you did B2, B1, most people would do B1, B2. If you do B1, B2, then you have to use commutativity to move the B1 next to the A1 and the B2 next to the A2. But if we write it as B2, B1, we're good. So the question is, do we actually need R to be commutative? So I'll let you think about that as to, do we actually need, if we had done the other proof, so the more standard, if did A1, A2 times B1, B2, then you need commutativity to get A1, B1, A2, B2 equals 1. But because you gave me B2, B1, things cancel very nicely, and we may not need commutativity. So again, it's always worth thinking about what you truly need versus what is convenient. Okay, so what if commutativity fails? So this is a question for you to think about. So for extra credit, do we need commutativity? Or is it just convenience or laziness? We're just so used to saying, oh, let's let R be What if we try to look at matrices? Matrices are a great example where we do not have commutativity. Would we be able to find a counterexample here? Or maybe not. What if we find that if you look at the set of invertible elements in 2 by 2 matrices, that forms a multiplicative group? Does that prove that commutativity is not needed? No, it just proves that that example still works. Maybe there's a more exotic example where commutativity fails and things break down. Okay, so the next is we need a result from number 3. And so this is the Euclidean algorithm. It's one of the greatest algorithms of all time. And it basically says if I give you 2 integers a and b, the greatest common divisor of a and b is the largest integer that divides both of them. I'm sorry. Yes, the largest integer that divides both of them. Is the greatest common divisor well defined? Yes. Does there have to be at least one positive integer dividing both a and b? Yes, and that integer is good. So we know the greatest common divisor is at least 1. Can you give me an upper bound for the greatest common divisor of a and b? The minimum of a and b. So we know the greatest common divisor is at most a, it's at most b, it's at most the minimum. So there's only finitely many things to choose. And so we can just look and see what is the largest number that divides both a and b. And we'll call that the greatest common divisor. Now, if I have the greatest common divisor, and I have another divisor of both a and b, does that have to divide the greatest common divisor? So the greatest common divisor is defined as the largest number that divides both a and b. If I give you another number that divides both a and b, by definition, does it have to divide the largest number? Why? But I'm just defining largest in terms of size. I'm not saying anything about factorizations.
Because of the main theorem of
So now it might be true, but you might have to do a little bit of work. By looking at unique factorization, every number can be written uniquely as a product of primes in increasing order. So what you might be able to do is go from the fact that the greatest common divisor exists to if you have any other common divisor of a and b, then it must divide the greatest common divisor. And that's another way to interpret the greatness of it. But just from the definition, we don't know immediately that any other divisor must divide the greatest common divisor. So there's a beautiful result, and this time we might talk a little bit about this. If I give you any 2 integers a and b, then there are some integers u and v such that a times u plus b times v is the greatest common divisor of ab. Not only do u and v exist, but we can find u and v extremely fast. The rapidity, the speed of this algorithm is one of the greatest of all time. It's what makes RSA encryption, what we saw in the first day of class, it's what makes it possible to do stuff like this in real time, is we don't have to go through all the possibilities. Can you give me a really painful way to find the greatest common divisor of a and b? Okay, so one possibility is you can assume you have the magic wand that allows you to factor numbers. You're a pure mathematician today, sure, you've got this wand, and you wave the wand and you factor a, you factor b, and then you look at all the primes, and in each prime you take the prime that occurs to you take the highest power in either a or b, and that number you can hopefully show is your greatest common divisor. Can you give me, now that unfortunately requires you to be able to factor. Can you give me another way to find the greatest common divisor? I'm sorry? It can still be painful, but this way it doesn't require you to know how to factor numbers. So that's using the Euclidean algorithm, that's being intelligent. So let's say the numbers are 2024 and 24601. Cultural extra credit if you know why I chose 24601. Les Miserables, yes, Jean Valjean. So 2024 and 24601. I want to find the greatest common divisor. I know it's at most 2024. So I can see does 2024 go into both? Good. So do I want to start checking at 1? No, yes, but instead of starting at 1 and going up, what should I do? Start 2024 and go down. Because if I check starting from 1, if I find something that's a divisor, okay, but then I have to still keep checking. Now, I could then remove that number from both of them. So if I find that 3 works, I can divide A by 3, I can divide B by 3, and play the game all over again. So there are things you can do to make the painful algorithms less painful, but there's still going to be a lot of pain. The Euclidean algorithm is there's a very fast way to find A and B. I mean, to find U and B. And one of the things that's nice is you can even limit yourself a little bit into the space of where U and B could be, but it's still a little bit painful. Looking at a lot of these proofs is a result that seems obvious, but is surprisingly not. And so years ago, sometime before 2017, because that's when the paper was published, Professor Silva was working on an analysis book here. And as I, like analysis and stuff like this, he was asking me for some comments. And we started to discuss, one of the great difficulties that we would, in a lot of these arguments, you want to use the fact that if a prime divides a product, then the prime divides either the first factor or the second factor or both. And it turns out it is a little bit of work to prove this. A lot of people accidentally assume things when they're proving this. Now, if you have unique factorization, this is not bad and hard to prove, but how do you have unique factorization? It's always making sure you do things carefully. Is this true if instead of a prime, I have a composite? So if M is composite and M divides AB, does M divide A or M divide B? So if a composite divides a product, does the composite have to divide at least 1? No. And then you want to search for good, counterexamples. Good example, what's a good composite number? So you could do 6. That's a possibility. What else could you do? And again, I care more about the thought process. There's nothing wrong with 6. What's the first composite number? 4. So, can I come up with a counterexample using 4? 4 divides. And so what I want is something where 4 does not divide either factor. So maybe each factor has a 2. 2 times 6, right? But 4 does not divide 2, and 4 does not divide 6. What if I gave you 6? Here's a fun way of doing it. 4 times 9. I mean, there's lots of examples you can do. But 6 does not divide 4, and 6 does not divide 9. So again, it's the thought process, how do I come up with these counterexamples? So this is an extremely useful fact. If a prime divides a product, then the prime divides either the first or the second factor or both. And if I have 2 numbers, A and B, I can find 2 other numbers, U and V, such that AU plus BV is the GCD of AB. Okay, and this is theorem 1.32 in the book. This was in chapter 1. So I urge you to go back and look at that. Happy to talk about this in greater detail in one of the problem classes and just do more on this one. So one of the consequences of this is this beautiful result. If we look at Z mod MZ star, this is the set of invertible elements. And it turns out that these are all the A's that are relatively prime to M. In particular, if P is a prime number, then Z mod PZ is a field. That just means the non-zero elements are all invertible. Because in that case, the only element that is troublesome is the zero element. Okay, so this is a great example. This is our clock arithmetic, coming back to play. What's going on? So let's assume first M equals P is prime. If A is relatively prime to P, must show A is invertible. Okay. Well, just a moment ago, I was mentioning this wonderful result that the greatest common divisor of A and B can be written in this form. There may be a reason why that was the slide right before getting to this. So we know for all B, there exists U and V such that AU plus BV equals the GCD of A and B. Can you give me a good choice for B? Take B equals what? I can think of only 4 possibilities. One of them is good, 3 of them are not. What would be a good choice for B? Any thoughts? So we're looking at the case when M is a prime P, we're giving you some A. What would be a good choice for B? We don't have that many quantities in play. What should we take? P, right? That's one of the quantities in play. The other thing is we could take B to be A, because we know A is in play. We could take B to be 1, because there is the multiplicative unit. We could take B to be 0. No, we can't take B to be 0, so that's not in play. So really, there's not that many possibilities for B. Let's try B as the prime. So we'll try B equals P. Then AU plus PV equals the GCD of A and P. But if A is relatively prime to P, what is the GCD? 1. Therefore, AU is congruent to 1 mod P. So A is invertible. And so we just proved that every element is invertible when M is prime. The proof is not that different in general. Assume M is an integer at least 2. I'm not going to really concern myself with studying Z mod 1 Z star. That's just it in the element. So now, if A is relatively prime to M, must show A is invertible. So for all B, there exists U and V such that AU plus BV equals the GCD of A and B. Take B equals. So what should we take B to equal? M. It's essentially the same proof as before. Take B equals M. Then AU plus MV equals the GCD of A and M, which equals 1. Therefore, AU is congruent to 1 mod M, so A is invertible. So this shows us that when we look at these clock groups, as long as we restrict to the elements that are relatively prime to the number of hours, they will be invertible. Great. Okay, so section 3.6 is quotient rings. I will just end with the definition of what a quotient ring is. So if I was a commutative ring, an ideal, I guess not, we won't get to the quotient, we'll just get to what an ideal is. An ideal of R is a non-empty subset. Why do you think we want a non-empty subset? So, do we want to consider something that has no elements? And again, sometimes these are pathological situations. So there might be one element we might want to always be present. So an ideal will have two properties. If A is in the ideal and B is in the ideal, then their sum is in the ideal. And if A is in the ideal and R is in R, then R times A is in the ideal. Why don't I have to also assert that R, in addition to R times A is in the ideal, why don't I have to assert that A times R is in the ideal? Because it's commutative, broken record, right? We keep assuming the ring is commutative. Always be careful, because there could be a situation where later on we don't say the ring is commutative. Not every ring, for us, every ring has an identity. People study rings that don't have identities. As a nice aside, do you know what a ring without an identity is called? Yes, you remove the I and it becomes a ring, R and G. That's a ring without necessarily having an identity. So can you give me a good choice for R? What would be a good choice for R? For little r? So we know that no matter what A we take, and no matter what R we take, if A is in the ideal and R is in R, then RA is in the ideal. What would be an interesting choice to take for R? Nope. Nope. Which identity? The multiplicative identity doesn't give you anything. What other identity could we take? The additive. So if we take R equals 0, so note R equals 0 implies 0 is in I as long as I is not empty. So as long as I has at least one element, then it has to have the 0 element. So the only possibility is I could take I could maybe define something where I have as my ideal something that has no elements. Okay, if I has no elements, is it true that if I take two elements in I and add them, that it's an I? Yes, because I can't take two elements in it. If I have no elements and I take something in A and multiply it by something in R, is that an yes? But again, why would I want to study something that doesn't exist? So for us, we will assume that it's non-empty. And now that we know it's non-empty, you can tell me at least one element that must be in it. What must that element be? Has to be 0. So we know 0 is always in the ideal because of how we've defined things. And so the question is then, what kind of interesting properties do ideals have? And one of the things we saw with groups is we could replace a group with a union of cosets. And the cosets came from taking a subgroup and doing nice things with it. Maybe we can do something similar with rings. Maybe there's a way to decompose rings into some kind of combination of simpler objects. And that's where the ideals will come into play. All right, so this is a good place to stop. I can get to the stopping.